Stage 2. And then we want to keep going, right? We want to draw stage 3. You'll find the drawing easier if you're not talking to each other, right? Easier to draw. It's easier to concentrate. Stage 3, I was looking over there. I didn't even look to the back there. I've given up on you guys. No. You guys were quiet this time, right? These guys were sitting here. Yeah. Okay, so we want stage 3. 3. It's a big piece of paper. Stage 3. And then we want to keep going. Stage 4. So, you know, I'm going to kind of start up here, I guess. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 4. 4. 4. Stage 4. You should be thinking about a fillet of fish right now. Stage 5 and 6. Well, let's see. Probably, can I fit 5? 5 probably won't fit in here. So might want to come down here. I'm going to move this up there. Whoops. It's attached. Okay, stage 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, 2, 3, 4, 5. And stage 6. Nope. Put that there. And there's stage 6. Okay. So how many dots made up fish stage 1? 6. Stage 2. Stage 3. Stage 4. Stage 5. Stage 6. Okay, now at this point we can't count anymore. We don't have the 7th stage, but how many will be in stage 7? And then, okay? So, what we're doing here basically is looking for a pattern, right? And human beings are pretty good at seeing patterns, recognizing patterns. So we've collected some data. We notice there's a pattern going on here. And we can use that to describe this relation. And the relation can be described in a number of different ways. So we've kind of drawn it on paper with diagrams. We've then made a table of values. with the growth stage and then the number of dots. We can also describe this with a set of ordered pairs. So what does the set of ordered pairs look like? So it's a set, you use a brace bracket, right? It's a set of ordered pairs. How are we going to write the first ordered pair? 1, 6. Then, okay, and so on. So you're just going to write out each set of ordered pairs from the table. Using set notation, right? So we're saying set consisting of and then we're going to end with a brace bracket on the end, right? Because we're drawing a set. So let's just finish it off. Okay, now if you think back to last year, remember the function is a relation where no two ordered pairs have the same x coordinate. Is the above relation also a function? Yeah. Okay. So none of these ordered pairs have the same x. They all have a different x value, right? So yes, period. Recall that the domain of a relation is the set of all possible values of the independent variable, which is which variable in this case? The x variable, right? What is the domain of this relation? Well, actually, we're just going to list it. Okay, so we're going to say, well, we're dealing with a finite relation. We're going up to 10 growth stages, and the domain consists simply of this set of numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Recall that the range of the relation is the set of all possible values of the dependent variable. What's the range of this function? Okay, so all we're going to do is list the dependent variable, which is which letter? The y value, right? So the y value depends. The number of dots depends on which growth stage you're in, right? So dots depends on growth stage. Note that the domain of this relation is the subset of natural numbers, right? So we have growth stage 1, 2, 3, 4. A function with a domain that is the subset of natural numbers is called a sequence. Since we know the domain of a sequence will always start at 1, 2, 3, right? You always got the first term, the second term, the third term, the fourth term, and so on. We concentrate more on the range of the sequence. So we're not too interested in the 1, 2, 3, 4, etc. We're interested in the range, the 6, 13, 20, 27, 34, and 41. So these are the terms of the sequence, right? The first 6 terms of which are 6, 13, 20, 27, 34, and 41. Okay. What is the first term of the sequence? 6. That's denoted by t and a subscripted 1, right? So we read this as t1 or t sub 1, right? T sub 1 as in the first thing of t. What is the sixth term of the sequence denoted by t6 or t sub 6? What's the sixth term? 41. How do we denote the 10th term? T10. Okay? And so when we say that, T10, you know, and we might say T sub 10, right, just to indicate that you're going to write the 10 as a subscripted number. What is the 10th term of the sequence? 69. Okay? Questions on that first page? So we drew a diagram, we drew these fish, we made a pattern, we recognized how the pattern was going. We saw that we could express that as a set of or as a table, as a set of ordered pairs. But we noticed that, hey, these ordered pairs always go 1, 2, 3, 4, the x values. So he says, forget those. We're just interested in the y values, the dependent variable. The relation between the growth stage and the number of dots can also be described with words. Complete the following sentence to describe how to determine the number of dots for a particular growth stage. So, to determine the growth stage, we're going to take, to determine the number of dots, take the growth stage and do what? So if I say, well, how do we get T10 just using the 10? Or how do we get T5 just using the 5 without having to go through the whole thing, right? Like 6, 13, 20. You know, so what about, what's T100? What's T50?
Times 7 minus 1.
Yeah, times 7 multiply. So determine, take the growth stage and multiply by 7. Then subtract 1. Okay, so if you look at them, you'd say, you know, the multiples of 7 are 7, 14, 21, 28. These are all 1 less than a multiple of 7. Right? So if we multiply by 7 and then subtract, let's fill this in, 1, subtract 1. Use your results to determine the number of dots for growth stage 20. Okay, so what do we go? We go 20 times 7 minus 1. 140 minus 1 is 139. So now we have a way of getting to how many dots would you need for any particular growth stage. Right? We got a formula, so we don't have to count our way up. Otherwise, we would have had to continue the pattern. Right? Growth stage 20. Well, you get 69, 76, and then 83, and then and keep track of where we are. And that's not really the best way to handle that. So how many dots are there in growth stage n? Yeah, 7n minus 1. That basically gives us a formula, right? We can find the number of dots in any growth stage using this formula. The general term of a sequence is denoted by t sub n. N is called the nth term. Okay, where n is any number we want it to be, right? I want n to be 20, then we do t20. I want n to be 100, we do t100. We're going to write an expression for the nth term of the sequence. So really it's just a formula, right? And this one says t sub n, the nth term is, and then here's our formula, right? We already figured it out, right? It's 7n minus 1. So when you're coming up with a formula for a sequence, you can check it against the sequence that you're given, right? If you're given a particular sequence, you got to try and figure out a formula for it. You can check by saying, okay, if n is 1, then t1 is 7 times 1 minus 1, which is 6. If n is 2, t2 is 7 times 2 minus 1, which is 14 minus 1 is 13. If n is 20, then it's 7 times 20, which is 140 minus 1, which is 139, right? So that my formula works. The general term of a sequence relates the term to the term number. Okay? So which term? I want term 20. I want term 50. I want term 100. Verify the expression for t sub n with the fifth term of the sequence. Okay, so let's start off with our formula. T sub n is 7n minus 1. I want t5. So everywhere I see an n, I'm going to write a 5. So it would be 7 times 5 minus 1. So t sub 5 is equal to 34. Okay, and show you get the fifth term. And if we go back to our sequence and look at the fifth term, it's 34. Well, this works both ways, right? So if I want to figure out how many dots in growth stage 5, I put a 5 in for n. But if I want to figure out if there are 559 dots making the perimeter, then which stage are we at? So we go t sub n is 7n minus 1. So always start with your formula, right? I have a formula. I'm going to substitute in. In this case, we don't know n, but we know what the nth term is. We got to figure out what n is, though, right? We know that some term in the sequence is 559. We want to figure out which term we're going to solve for n. So let's add 1 to both sides. Get 560 is 7n. Divide by 7. You get n is 80, so we are at growth stage 80 if there are 559 dots. Okay, so in this case, we know the nth term, we just don't know what n is, right? So we're going to work it out, and we use the formula, and we substitute in for the nth term, and we solve for n. One thing we know is this has to solve to be a natural number, right? Because the n values can only be 1, 2, 3, 4, 5, 6, right? They're terms. You can't get a value of 17.5, right? It's not the 250.7th term in the sequence, right? It'd be 250, 251. So, sequences. A sequence can be thought of as an ordered list of objects. So 5, 8, 11, 14, 17, 23. They're in a particular order. 2, 6, 8, 54, 162, 1, 1, 2, 3, 5, 8, 13, 21. The first term of the sequence is denoted by T1 or T sub 1. The nth term is denoted by Tn or T sub n and is called the general term. Okay, so we're talking the general term because we can use it to calculate any specific term. I want term 200. Fine, we're going to take the formula for the general term, put a 200 in for n, and find you that term. A sequence can have a fixed number of terms. That's finite. So this one ends, right? 5, 8, 11, 14, 17, 20, 23. Or it can be infinite. This says 2, 6, 8, 54, 162, and the 3 dots. The technical name for which is? Anyone? Ellipsis. Ellipsis. So that means that it keeps going, right? And so on. Or just keep going with the same pattern, right? So you can continue. It says continue the pattern on. So if you're going to use those 3 dots, you have to give enough information for somebody to figure out the pattern. Classify the above sequences as finite or infinite. So which one's which? What's this one? Finite. And the other 2 are? Okay, so that's one way to classify a sequence, right, as to whether it ends or it doesn't end. It's finite or infinite. Okay, questions on this page? No, as far so good. Types of sequences. For each sequence, describe a rule for how to get from one term to the next term and write the next 2 terms. Actually, I think what we should probably do is let's write the next 2 terms, right? Because we can look at that and kind of figure out what the next 2 terms are, and then we'll state the rule. So 24, 29, 34, 39, what's next? 44, and what's the rule? Add 5, right? So the rule is to add 5. 18, 20.5, 23, 25 and a half, what's next? 28, and 30.5. What's the rule? Add 2.5. 12, 5, negative 2, negative 9, negative 16. So subtract 7. 5, 10, 20, 40, 80.
Times by 2 minus 1.
And what's after 80? How do you get to the next term? Multiply by 2. 7, negative 21, positive 63, negative 189. So we might, this time I would say what we're doing because we got to get calculator out to figure out what's next. So multiply by -3. So what's after -189? How much? 567. What's after that?
-1701.
84, 42, 21, 21 over 2. What are we doing? Divide by 2. That gets a little tough when I get here, so I'm going to phrase it as multiply by 1/2. Gives me 21 over 4 and 21 over 8. Right? If you say divide by 2, that's easy to do. 84 divided by 2 is 42. Divided by 2 is 21. Divided by 2 is 21.5. Divided by 2 is, right, now I'm trying to divide a fraction, so I'm just going to say multiply by 1/2. Right? It's the same as dividing by 2. 1, 1, 2, 3, 5, 8, 13, 21.
40.
Nope. 34. What's after that? What's the rule? So what did you do to get the 34? Add the 2 previous terms. Anybody know what that sequence is called? Yeah. Not called ellipsis, but that can be your word for the day. Close. What's it called? Well, it was in there, but what's it called? It's not Da Vinci. Close. Fibonacci. It's called the Fibonacci Sequence because it was developed by a guy named, wait for it, Fibonacci. Also known as Leonardo of Pisa. Okay, well the boys in the back draw some parallels between this and something else. Number 19. What? Oh, okay, there you go. Sequences where the same number, positive or negative, is added to each term to create the next term are called arithmetic sequences. So there's first few, right? We're saying, well, okay, you add 5, you subtract 7, you add 2.5. Those are called arithmetic sequences. So which of the sequences in question 18 are arithmetic? Where are we adding or subtracting the same number? A, B, C. The sequence 12, 16, 20, 24, 28, comma, ... is an infinite arithmetic sequence. State the difference between the following consecutive terms. So what's 16 minus 12? 4. What's 20 minus 16? What's 24 minus 20? What's 28 minus 24? 4. Right? You wouldn't even have done that. If I just said, what are the next 2 terms? You would have said 32, 36, right? You wouldn't have thought, well, 16 minus 12 is 4. You would have just said, well, okay, obviously I'm adding 4 each time, right? Now, but the way you get that is by actually going 16 minus 12. What's the difference between 12 and 16? 4. What's the difference? How do I get from 16 to 20? Add 4, and so on. For arithmetic sequences, the difference between consecutive terms is constant. This constant is called the common difference and is denoted by the letter D. For the sequence 12, 16, 20, 24, 28, the common difference is 4. State the common difference for the arithmetic sequences in question 18. So what's the common difference for A? What's the common difference for B? And what's the common difference for C? Okay? So if we're adding, the common difference will be positive. If we're subtracting, the common difference will be negative, right? Sequences where the same number is multiplied to each term to create the next term are called geometric sequences. Which of the sequences in 18 are geometric? D, E, anything else? F. The sequence 2, -8, 32, -128 is a finite, right? It comes to an end, there's no ellipsis on the end. Is a finite geometric sequence. State the ratio of the following consecutive terms. What's -8 divided by 2? -4. What's 32 divided by -8? What's -128 divided by 32? Note that for geometric sequences, the ratio, right? Ratio you're dividing, right? Difference you're subtracting, ratio you're dividing. The ratio of consecutive terms is constant. This constant is called the common ratio for some strange reason. And it's denoted by the letter R. For the sequence 2, -8, 32, -128, the common ratio is -4. State the common ratio for the geometric sequences in 18. So what is it for D? 2. For E? -3. And for F? 1/2. In an arithmetic sequence, each successive term is formed by adding a constant to the previous term. The constant is called the common difference, and it's equal to T2 minus T1, T3 minus T2, and ultimately T sub n minus T sub n minus 1. So if this is the 100th term, this will be the 99th term, right? So in other words, it's take any term and subtract the term that precedes it, the preceding term, you'll get the common difference. In a geometric sequence, each successive term is formed by multiplying a constant to the previous term. This constant is called the common ratio and is found by taking T2 divided by T1, T3 divided by T2. In other words, take any term divided by the preceding term. So ultimately it becomes T sub n, the nth term divided by the n minus 1. If this is term 50, this is term 49. Now when we look at it, usually we just kind of look at it and say, oh, multiply by 2, multiply by 2, multiply by 2. Really what you're doing is you're actually taking this term and dividing it by that term to get what you're multiplying by, right? But we kind of look at it automatically. We just sort of think that's what's happening. We don't go through the thought process of that's what I did. Some sequences are neither arithmetic nor geometric. Which of the sequences in question 18 is neither arithmetic or geometric? G. The sequence is called the Fibonacci sequence and has a large number of applications in nature. So you'll find it in pine cones, you'll find it in pineapples, in the head of a sunflower seed, and the way that the things are arranged. Okay, different arrangements. So maybe if we finish this and have some time, there's a quick little video on the Fibonacci sequence where you can kind of see that this particular pattern of 1, 1, 2, 3, 5, 8, 13, etc. carries on. Hey, I guess we'll have some time. But the next thing we want to do is we want to look at yet another, which is just classifying sequences. So pretty short. There's no, you don't have this, but we're just going to figure it out. So 27, 21, 15, 9, what kind of sequence is that? You got arithmetic, geometric, or neither? Arithmetic, right? What's the common difference? -6, right? Subtract 6. 1, 4, 9, 16, 25. So here's the easy way to figure it out, right? If it's arithmetic, you're going to add 3, which makes the next term 7, and it isn't. If it's geometric, then you're multiplying by 4, which it isn't. So it's neither arithmetic nor geometric, right? You can also do it by going 4 minus 1 is 3, 9 minus 4 is 5. They're not the same. 4 divided by 1 is 4. 9 divided by 4 isn't 4. They're not the same, so it's neither arithmetic nor geometric. 256, 192, 144, 108, 81. So are we subtracting the same number each time? So what's 192 minus 256? I'd go more 64, I think, negative 64. If I subtract 64 from 192, do I get 144? No. So not arithmetic. Okay, what's 192 divided by 256? What's 144 divided by 192? Is it the same as what you got? What's 108 divided by 144? Is it the same as the 2 that you just got? Yeah. What kind of sequence is it? Geometric. 5, negative 5, 5, negative 5, negative 5. So if a sequence ever flips signs, right, positive, negative, it can't be arithmetic, right? Because you can't be adding or subtracting. So what's negative 5 divided by 5? What's 5 divided by negative 5? What's negative 5? Negative 1. So it's geometric. 1, 1/2, 1/3, 1/4, 1/5. Neither. Okay? How would you get there? You can look at it, right? Because you just look at it and say, okay, if it's arithmetic, then 1 minus 1/2 gets me 1/2. Minus 1/2, the next term should be 0. It's not. If it's geometric, then 1 times 1/2 gets me 1/2. That should be 1/4, and it's not. So it's neither. 2, 2 squared, 2 cubed, 2 fourths, 2 fifths. Geometric, right? How do we go from one term to just multiply by 2, right? Because we're increasing the powers of 2. Oh, here's one we get to get you thinking a bit. 3x plus 2y, x plus 5y, negative x plus 8y. So if you subtract 2x and add 3y, subtract 2x takes you to x, and add 3y, we get 5y. Subtract 2x, go to negative x, add 3y, we get. Subtract 2x goes to negative 3, add 3. Yeah. So what is it? Arithmetic, right? We're adding the same thing to each term. Okay? Formally, how would you do that? You would say, okay, what's x plus 5y minus 3x plus 2y? Okay, which is x plus 5y minus 3x minus 2y, which is negative 2x plus 3y. And then you do it again, right? You go with negative x plus 8y minus x plus 5y. Okay, and you'll get the same thing, right? Which will tell you, oh, okay, it is arithmetic. Right, and if you want to verify, you can do one more. Right? Or once you've got this, you can just say, okay, well, what if I subtract 2x and add 3y? Yeah, what if I subtract 2? Yeah, I'm going to get the next terms, right? State the first 4 terms of each sequence. Okay, if T1 is negative 19 and the difference is 7, then what's T2? And what's T3? And what's T4? Okay. T1 is 12 and R is negative 3. What's T2? What's T3? What's T4? Okay. So D is the common difference, which says you add or subtract, right? In this case, we're adding. R is the common ratio, which says you multiply. Okay, if this is an arithmetic sequence and you go from 16 to 8, what comes next? And what came first? If this is geometric and you go from 16 to 8, what comes next? And what came first? Okay, good. Right? That's it.